Hello, my name is James Bongiovanni, and I will be giving you a chapter review for sections 1 through 3 of ME 302 Thermodynamics. The way I decided this would be best laid out is to just go over all of the key terms and explain everything step by step, because if you can understand the key terms, then the formulas will just sort themselves out. It's all going to be plug and chug. So to start off with, we'll go with the first law of thermodynamics, which simply states energy cannot be created or destroyed, it only changes forms. This is the foundation of all of thermodynamics. Then we have open systems and closed systems. So in any question that you're asked, it will either be an open system or a closed system, depending if it is mass is going to be coming in or leaving the system, or if it's like a rigid container that doesn't let anything out. That's just as simple as that. Extensive and intensive properties. So the best way to tell if something's going to be extensive or intensive is if you cut it in half, will the number change? So you'll see in the case of extensive properties, it's dependent on mass, like volume, internal energy, mass. So if you were to cut that in half, then it won't have as much of it as it was before. But if you have something that's intensive, like density, temperature, or mass, if you cut it in half, then it still has the same density. If you cut a piece of gold in half, it's still just as dense as its other piece of gold. State postulate. A system can be fully defined with two independent intensive properties. So if you are given two intensive, remember intensive means it's independent of mass, you can figure out everything else about the system, which is what we're going to have to do for most of our equations and questions in class. Dimensional homogeneity. All formulas in math, ever, physics, doesn't matter what it is, the units on the left side will equal the units on the right side. It has to. That's just the basics. That's why, especially if you see constants, they have a whole bunch of different weird different units inside them. That's to make the whole system homogeneous. Temperature scales. So here you'll see we have Celsius, Kelvin, Fahrenheit, and Rankine scales. The Kelvin scale is an absolute scale that goes from basically zero internal energy in the system all the way up to infinite energy. Obviously, 0 Kelvin is absolute zero, and it's impossible to attain, but that's the basics in an absolute temperature that we use for all of our equations to make everything come out in an even keel sort of way. So Celsius, if you're given Celsius, all you have to do is add 273.15 degrees, and then you're in Kelvin. And for Fahrenheit, it's the same process. If you're in Fahrenheit and you need Rankine, you just add 459.67 degrees. It's an easy conversion. And since we've all made it to the point where we're this far in engineering, I'm sure we know how to calculate from Celsius to Fahrenheit. I'm not going to go over that. Specific weight. Rho times G. You will sometimes see it as a symbol that looks like gamma. And this is usually a shorthand for if you're going to use, say, Pascal's law. All you would need is this times height, and it's the exact same thing as saying rho times G times H. It just combines these. Moving right along, specific gravity. Sometimes in an equation, it'll give you the specific gravity of a fluid. All it's saying is that the number they gave you is the fluid's density divided by the density of water. Process, path, cycle. So a process, changing equilibriums from one state to another. So if it goes from one temperature in a volume and it comes up to a different pressure in a volume, P, V. If it goes from this state to this state, then we say that this was the process at which it went from this state to this state. The path would be the line from the two. A cycle is if you go from point 1 to point 2, then you come back again to point 1. That's a complete cycle. So your initial state is going to be the exact same as your final state. just like a cycle of an engine, which would be more complex. You'd see something like this, roughly. Isothermal, isobaric, isochoric. Simply put, over the course of the entire process, you're either going to have constant temperature, meaning that your pressure and volume will change, or you could have constant pressure, where temperature and volume will change, or constant volume, in which temperature and pressure change. But for all of our systems, it's going to be a combination of constants and variables with these three here. The zeroth law of thermodynamics. So if two bodies are in thermal equilibrium with a third, they are all in thermal equilibrium, which it sounds intuitive and it makes sense, but it's a foundational piece of knowledge for everything that we're going to be learning in this class. So we'll say we have two rocks, and we'll say they're actually touching. All right, so here's rock 1, rock 2, and we leave them to the atmosphere, which is piece 3. If this piece and this piece were once at different temperatures, but now they're at the same temperature, then 1, 2, and 3 must all be in thermal equilibrium. And that's the zeroth law of thermodynamics. Absolute pressure versus gauge pressure. This might get kind of confusing, and you have to pay close attention during your questions that you get asked, because it can really mess up your numbers. Usually, because the numbers will be so different, you'll be able to see something's wrong, but you have to make sure that especially for the small stuff, you pay close attention. So if it says that you have 30 kilopascals, all right, that's gauge. What it's really saying is that its absolute pressure will be 101 more than that, because your 101 is your atmospheric pressure. So what you really are dealing with is 131 kilopascals. So one way to think of one way to think of absolute pressure would be, this is the pressure from a vacuum. From a vacuum's perspective, this has 131,000 pascals as opposed to a vacuum. 30 gauge is simply saying that it's 30 more than the atmosphere. And Pascal's law, as mentioned earlier, rho GH, hydrostatic pressure. This will come into a lot of our fundamental questions. If you have a serpentine kind of hose that goes into like a tube, and you want to know what the pressure is at any given point, or from here to here, if you even have different fluids going the whole way across, then you can determine the hydrostatic force of each point and get your way all the way to pressure 1. And that's the fundamental of that. And I will see you in chapter 2. All right, now we're in chapter 2. I'm going to drag this down a little bit so we can go step by step. So in the last slide, we talked about E in minus E out equals E total of the system. So now, what is E? Well, we have two types. We have macro energy and micro energy. Macroscopic, microscopic. Macro energy has to do with velocity, potential energy, things you can actually see, hold, and influence yourself. Micro energy has to do with the influence or the energy of the subatomic particles. Usually it's noted as heat. So here we see that there. So for mechanical energy, E dot, I can't actually put a dot on top of these, otherwise it'd look weird, so I just wrote dot to be more professional. The dot is per time. The lowercase e signifies that it is intensive, or it's independent of mass. So that will not change depending on the system. That's why you have to multiply it by m. If it's uppercase, then it's extensive. It already has mass accounted for in it. So you can formulate this also from saying your m dot, or your mass per second, multiplied by your pressure divided by your density of your fluid, or whatever your system you're dealing with is, plus your velocity squared divided by 2, which is just like a direct reference from 1/2 mv squared, our kinetic energy formula, and then our gravity times z, or elevation, which is our potential energy. So if you look, you'd have your 1/2 mv squared plus mgh times mass times pressure divided by density. And that will give you your total mechanical energy of your system. Another important key point is my right little thing there. Work. So work is going to be force times distance, which we've all learned back in basic physics. And a system can possess energy, but it cannot do work. So how much work is in the system is an irrational question. It doesn't make sense. You can't just say, well, how much work is inside of a piston? People are going to look at you like you're an idiot. How much work does the system do? How much is the piston going to push? How far does it travel to compress a gas? Those are the appropriate questions you need to ask yourself. However, you can say how much energy is inside the piston at any given point in time. And that's primarily what we deal with in thermodynamics. Mechanisms of heat transfer. So in Chapter 1, we talked about open systems and closed systems, depending on if mass was coming in and leaving the system or if it was constant throughout the whole system. And mechanisms of heat transfer can affect both open and closed systems. So even if your mass can't leave a container, heat can still come in and leave. Work can still be done on the system, but mass flow will only have to do with open systems. An adiabatic system is a system that does not exchange heat with its surroundings. So, like a thermos, it's insulated. Conduction, convection, and radiation are the three types of heat transfer. We talked about them briefly, but it's not going to be covered in much detail in this class. But to paraphrase, it's always, heat is a transfer of energy. So for conduction, that'd be like if you were to take your hands and rub them together really hard, you feel the friction. That's conduction. It's direct contact from solid to solid. Convection would be like if you put your hand inside the oven and you could feel the heat up from the coils. It's moving from a solid to the fluid, being the air, and then from the air to your hand. So that's how convection works. It goes from a solid to a fluid or a fluid to a solid. Radiation comes in many shapes, sizes, forms, primarily electromagnetic waves and particles and or photons. So you've heard of gamma rays, which are like more solid particles. It's actually like something that will knock your DNA cells away. And then they have stuff like photons, which so that'd be like infrared or ultraviolet. It's traveling photons, and it can also infect the environment around you, like give you sunburns or just feel like heat, as in infrared. So in the last chapter, we talked about paths, cycles, and processes. So for a cycle, as mentioned before, your initial energy is the same as your final energy. So the work out will equal the work in a perfect system. Shaft work is somewhat along the same lines as torque. It has to do with if you have an object like that has a radius and it's turning, then your shaft work will be a function of both the radius and how fast it's moving and how much work is being done, or how much force is being done on everything as a whole. Non-mechanical work. We have three major types. Electrical, so things done with AC, DC, etc., etc. Magnetic work would be if you have, say, a south pole pushing another south pole away. It's exerting energy on the other magnet, it's pushing it away. Electrical polarization, better known as electromagnetic force, is electrically powered magnet. It only works if there's power or current moving through. It can be done by taking a copper wire and wrapping it around a nail. Give it a current with a battery, suddenly you can attract paper clips with it. Once the current is removed, the paper clips fall. Performance is similar to efficiency. So in physics, we also learned about if your engine's doing this much work with this much energy you put into it, whether it's gasoline or electrical, how much energy are you getting out of it that you put into it? This is not a perfect world. You will never have 100% efficiency. So similar to that, we have performance. So if you have a desired output you have to divide it by the required input, and that's going to be, you take this basic formula and we use it to calculate things like mechanical pump and turbine efficiency. What you have to remember, those in this formula, pumps put energy into the system and turbines will take energy out of the system being the fluid moving through it. And that concludes Chapter 2. I will see you in Chapter 3. Chapter 3 is going to primarily deal with the use of the charts, pressure volume charts, temperature volume charts, the different phases of the solids and liquids and gases, and how they interchange and how they exchange energy. Everything we talk about when we're doing these transfers of energy will be dealing with pure substances. So water, air, refrigerant, R134A, it's all going to be considered a pure substance. It's a fixed chemical composition. It doesn't change from one part of the system to another. There are three major phases, and one we won't be concerned with. Solids, very low energy state, very little intermolecular movement, which is why you don't really see solid objects rattling apart, or how they hold their shape so well. They're very rigid. Liquids are at a higher energy state. They have freer intermolecular movement, so they can take the shape of their containers, and so on and so forth. Gases are very high energy states, very excited intermolecular movement. They bounce around all over the place. They have perfect elastic reactions. Won't be concerning ourselves with that. Those are the three phases. Plasma has to do with lightning bolts, and it gets wonky, so we'll move right along. On our charts, we'll see saturation temperatures, saturation pressures. Saturation temperature is when your liquid, so we'll say water for an example. Liquid water will begin to turn into a vapor at its saturation temperature. Same idea, same chain of thought. Saturation pressure is the pressure at which, at a given temperature, that the liquid will begin to boil and turn into a vapor. So now we'll discuss more about these changes of phases. There will be five we're most concerned with. Compressed or subcooled liquids, that's just like a cup of water you have on your desk. It's not about to vaporize. It's not about to boil. It's happy where it is. Saturated liquid is about to vaporize. We'll say at sea level, its water is at 100 degrees Celsius. It is about to boil. Saturated liquid, it will keep this same temperature, but more and more energy will be being put into the system. But the temperature will not increase at all. Its pressure will not increase at all. It just stays constant until it gets to a certain point where the volume can finally break out of that, and everything that's in the inside of the container that was liquid is now gas. And then that's a saturated vapor. It's not about to condense. It's at the opposite end. So if we have that little hump like this, you'd see that this is going to be your subcooled liquid. Right here is going to be your saturated liquid. It's right there on the line. From here to here is going to be your vapor mixture, where it's both coexisting with liquid and vapor. Along this line here is when it's a saturated vapor, and it's not about to condense. So you put more energy into the system, and you'll see it take off, and now it's superheated. I will use latent heat to describe the fusion vaporization. So in general, energy is absorbed when moving to a higher energy phase and released when moving to a lower energy phase. So water will release energy when it turns into ice, and it will absorb more energy when it turns to a steam or a vapor. And that's what you'll see with latent heat. It's the energy amount that's being released or absorbed during the change of phase. So in the case of fusion, this has to do with solid materials, say metals. It has to do with the melting and the freezing, so when it becomes a solid metal or a liquid metal. And then you have the latent heat of vaporization, which is the same process mentioned above with the water. It's going to be absorbing energy when it goes to steam, and it's going to be giving it energy up when it goes to a lower phase. So in some diagrams, you'll see a chart will show solid, liquid, and gas phases, something like this. And at this point where everything intersects, it's called a triple point. So here you could have liquid, gas, and solid all living happily together at this one temperature. and that's called a triple point. Sublimation is when you have something like dry ice, and it goes from its solid dry ice material and it goes directly to a gas. It just starts shrinking and shrinking, and it's changing phases immediately. It doesn't need to go through the liquid phase because it's too hot for the liquid carbon dioxide to stay where it's at. The compressed liquid approximation states that the energy of a subcooled phase, as in water that's not about to boil, water that's sitting next to you on your desk, is its energy state is the same on the chart for any at that temperature. So if you look up water at 30 degrees C, it will be at a certain energy level, and that's the same for all liquid at that temperature, approximately. And then the formulas we see here, those are just the ideal gas laws. Again, we learned that in chemistry, we learned that in physics. I'm not going to go over that. That concludes my period of instruction. Thank you for your time.